Hey there. Welcome back to the deep dive. Picture this for a moment. You're living in the very bottom of, well, a vast invisible ocean, this incredible blanket of air we call the atmosphere. Everything we experience out here, all our weather, all our climate patterns, it's all fundamentally powered by energy. And where does almost every single bit of that energy come from?
It's the sun, yeah.
Yeah.
It's really the engine driving the whole system.
Exactly. So Earth receives this enormous flow of energy, but it doesn't just keep building up, right? Our planet has this remarkable ability to radiate energy back out into space, maintaining a delicate balance. It's this constant dance, energy coming in, energy going out, that keeps the planet's temperature, relatively stable over these huge timescales. So, for this deep dive, we're going to roll up our sleeves and really dig into the source material you've brought us on solar radiation, heat balance, and temperature. Our mission basically is to pull out the crucial insights and figure out how the sun's energy fuels our atmosphere, how that creates the temperatures we feel every day, and how the Earth manages this incredible balancing act with all that energy flowing through.
And honestly, getting these core ideas is just foundational. It's the bedrock for understanding why we see such massive differences in weather and climate from, one place to the next around the world. This material gives us a really detailed look at those fundamental processes.
Okay, let's unpack this then. It all kicks off with that powerhouse in the sun. The energy arrives here as incoming solar radiation, or what we often call insolation.
Right.
It travels across space and reaches us mostly as short wavelengths.
Right. Insolation is just that.
Okay.
The incoming solar radiation in its shortwave form. And, even though Earth is this huge sphere compared to the sun, we only intercept a minuscule fraction of its total energy output.
Yeah, tiny.
But like you said, even that tiny sliver is immense.
Yeah, I saw a number in the material on average. At the very edge of our atmosphere, Earth gets something like 1.94 calories per square centimeter every minute. That's a ton of energy hitting the system constantly.
It is. And here's a fascinating little detail about that incoming energy. The actual amount Earth receives, it varies slightly during the year.
Oh, right. How so?
It's because our orbit around the sun isn't a perfect circle. It's elliptical. So when Earth is farthest away, which we call Aphelion, that happens around July 4th, about 152 million kilometers out.
Okay.
Then when we're nearest, Perihelion, that's around January 3rd, about 147 million kilometers away. So technically, the total insolation hitting the planet is slightly more when Earth is closest in January.
Now, here's something I find really interesting, though. If we actually get more total energy input in January, which is winter for us in the Northern Hemisphere, why doesn't that make a huge difference to our daily weather compared to getting slightly less energy in July?
That's a great question, and it really gets to how the whole system works. That small variation, the one from the Earth-Sun distance, it's largely masked, overshadowed by other much bigger factors when it comes to our day-to-day experience of temperature down here at the surface.
It's like what?
Well, things like the massive difference in how land and water heat up and cool down, or the huge patterns of air and ocean circulation moving heat around those, have a much, much more dominant effect on local weather than that slight orbital variation does.
Okay, that makes sense. So the total energy hitting the top is pretty consistent day to day, but the amount that actually reaches the surface where we live, that changes dramatically depending on where you are, what time of day, what time of year, what causes that huge variation in surface insolation.
Well, several factors are key. The most obvious one is just Earth's rotation, day and night. Simple enough. Facing the sun, you get energy. Facing away, you don't.
Right.
But probably the most significant factor is the angle the sun's rays hit the surface. And that's tied directly to your latitude.
Ah, latitude. Okay.
Yeah. Near the equator, the sun is often high overhead, so the rays hit almost vertically. But as you move towards the poles, the angle gets much lower. The rays come in much more slanted.
Right, like shining a flashlight straight down versus tilting it way over.
Exactly that. And that slant angle, it has two big effects. First, the same amount of incoming energy gets spread out over a much larger area on the ground, so less energy per square meter. Right?
Okay, yeah, thinner spread.
And second, those slanted rays have to travel through a longer path in the atmosphere to reach the surface, which means there's more opportunity for that energy to get absorbed or scattered by stuff in the air before it even gets down. This is really the main reason why tropical regions get vastly more solar energy over a year than the polar regions do. Now, other things play a role too, though they're generally less dominant globally. The length of the day, obviously longer days mean more time to soak up sun. How clear or cloudy the atmosphere is, that's huge too. And even the shape of the land, the configuration, can make a bit of difference locally.
Okay, so the sun's shortwave energy is zipping towards Earth. What happens as it makes its way through that atmospheric ocean before it hits the solid ground? Is it just a straight shot down?
Not quite. I mean, the atmosphere is actually pretty transparent to most of that incoming shortwave radiation, which is why we feel the sun's heat, right?
Yeah.
But some of it does get absorbed on the way down. Things like water vapor, ozone, other trace gases, especially down in the troposphere, the lowest layer. They absorb some of the near-infrared parts of the spectrum.
And what about all the light we do see? You know, the bright blue sky we get on a clear day, or those incredible reds and oranges at sunrise and sunset. Where does that come from?
That's all about scattering. As the incoming sunlight hits tiny particles suspended in the atmosphere, we're talking air molecules, dust, aerosols, that sort of thing, it gets deflected, scattered in all directions.
Okay.
And different wavelengths or colors of light are scattered differently. It turns out that the molecules in the air are really good at scattering the shorter wavelengths, the blues and violets. That's why the sky looks blue during the day. That blue light is being scattered all around.
Makes sense.
And at sunrise or sunset, the sunlight has to pass through much more atmosphere to reach your eyes. By the time it gets to you, most of the blue light has been scattered away, leaving the longer wavelengths, the reds and oranges, to dominate what you see.
Cool. Okay, looking at the planet as a whole then, where does the most solar energy actually reach the surface and where does it get the least?
Well, as you'd kind of expect from that angle effect we talked about, there's a huge difference. You go from the tropics, where you might see average insolation around, say, 320 watts per square meter,
Wow.
all the way down to the poles, where it might only be around 70 watts per square meter. Big difference. But here's a slightly surprising twist that the material points out. The absolute maximum insolation received at the surface isn't typically right at the equator.
Oh, where is it then?
It's usually found over the subtropical deserts.
Really?
You know-
Deserts, why? I'd have thought the equator, highest sun angle.
You'd think so, but the key factor is clouds. While the sun angle is often highest near the equator, that region also tends to have a lot of persistent cloud cover, especially in the afternoons. Those clouds reflect a significant chunk of the incoming radiation back to space before it even reaches the ground. Subtropical deserts, on the other hand, are famously cloud-free most of the time. So even though the sun angle might not be perfectly overhead as often as at the equator, the lack of clouds means a much higher percentage of the incoming energy actually makes it through the atmosphere to the surface day after day. So overall, the deserts get more net insolation hitting the ground than the often cloudier equatorial regions.
That's really interesting. Clouds make a huge difference.
They really do. And we see other patterns too, like land masses generally receive a bit more insolation than oceans at the same latitude, partly because oceans tend to generate more clouds. And obviously in winter, the middle and higher latitudes receive drastically less energy than in summer shorter days, much lower sun angles.
Okay, so the sun's energy reaches the Earth's surface, warms it up, great. But the air above us isn't heated directly by those incoming shortwave rays, is it? How does our atmosphere actually get warm?
That's a crucial point. The atmosphere itself, well, it's not heated very effectively by that incoming shortwave solar radiation. Instead, the Earth's surface, once it gets heated by the sun, it becomes a radiator itself.
Okay.
It starts emitting energy, but at much longer wavelengths. This is called terrestrial radiation, or sometimes long-wave radiation. And this long-wave energy rising up from the surface is what primarily heats the atmosphere, essentially from below.
Ah, I see. So the ground heats the air, not the other way around, directly from the sun.
Pretty much, yeah. And this is where greenhouse gases become really important. Gases like carbon dioxide, water vapor, methane, they are really good at absorbing this outgoing long-wave terrestrial radiation.
Right, the greenhouse effect.
Exactly. When they absorb that energy, they warm up, and then they re-radiate heat in all directions. Some goes back down towards the surface, keeping it warmer than it would be otherwise. And crucially, some also gets radiated upwards, eventually escaping out to space, which helps maintain that overall balance we talked about. Now, besides radiation, heat also moves around within the atmosphere in a few other key ways.
Okay.
There's conduction. That's heat transfer by direct touch, molecule to molecule. It's really only important for warming the very, very thin layer of air that's directly in contact with the warm ground.
Okay, tiny layer.
Yeah, very localized. Then there's convection. This is the vertical movement of heat. Warm air near the surface becomes less dense, it rises, carrying heat upwards, and cooler, denser air sinks to take its place. Think of like bubbles rising in boiling water, or hot air rising from a radiator. This is a big deal, especially in the troposphere.
Got it. Vertical movement.
And finally, there's advection. This is the horizontal movement of heat by moving air, which we usually just call wind.
So wind is basically just heat being carried sideways across the planet.
Essentially, yes. It's transporting air with a certain temperature from one place to another. And the material points out something important. This horizontal movement, advection, is actually relatively more important than the vertical movement, convection, especially when we're talking about those day-to-day temperature changes and weather patterns, particularly in the middle latitudes.
Really? More important than rising warm air?
For driving regional weather changes, often yes. A good example they give is the Lu, those famously hot, dry winds that blow across parts of northern India during the summer. That's a perfect example of advection. It's just hot, dry air being transported horizontally over huge distances, drastically changing the temperature where it arrives.
Okay, that makes sense. So this brings us right to the heart of the balance idea, the Earth's heat budget. How does our planet manage to not just get hotter and hotter or colder and colder with all this energy constantly flowing in and out?
That's the whole concept of the heat budget. Over the long haul, for the planet as a whole, the total amount of energy the Earth system receives from the sun has to be balanced by the total amount of energy it loses back to space. It's this equilibrium that keeps the average global temperature relatively stable.
So how does that math work out? Can we track the energy flow?
Yeah, we can. The source material uses a neat model. Imagine 100 units of incoming solar energy arriving at the top of the atmosphere.
Yeah, 100 units in.
Right. First off, about 35 of those units are immediately reflected straight back to space before they even get a chance to heat anything up. This is the Earth's overall reflectivity. It's albedo.
Albedo, right.
Clouds are the biggest player here, reflecting about 27 units. Bright surfaces like snow and ice reflect maybe 2 units, and a few units just get scattered back to space by the atmosphere itself. So boom, 35 units gone right away.
Okay, 35 reflected, leaving 65.
Exactly. So 65 units actually enter the Earth atmosphere system and get absorbed somewhere. About 14 of those units are absorbed directly by the atmosphere itself, by those gases and water vapor we mentioned earlier.
Okay.
And the remaining 51 units make it all the way down and are absorbed by the Earth's surface, the land, and the oceans.
All right, surface absorbs 51 units. What happens to that energy then? Does it just stay there?
Nope. The surface warms up, and then it radiates those 51 units back upwards, but now as that long wave terrestrial radiation.
Got it. Radiating heat back up.
Now, where do those 51 units go? Some of it, about 17 units according to the model, manages to pass directly through the atmosphere and escape straight out to space, like going through an atmospheric window.
Okay, 17 units out.
The other 34 units of that outgoing terrestrial radiation get absorbed by the atmosphere. This happens through a few mechanisms. Some is direct absorption by greenhouse gases. Some heat is transferred upwards via convection and turbulence, those rising air currents. And a significant chunk, about 19 units in this model, is transferred via latent heat, the energy released when water vapor condenses into clouds.
Latent heat, right. Energy hidden in water vapor.
Exactly. So let's tally up what the atmosphere absorbed. It got 14 units directly from the incoming sunlight. And then it absorbed another 34 units coming up from the Earth's surface. So 14 plus 34 equals 48 units absorbed by the atmosphere in total.
Okay. Atmosphere holds 48 units.
So what does the atmosphere do with that energy? It warms up, and then it radiates those 48 units away.
Yeah.
Back out to space.
Ah, okay.
So now let's track all the energy heading back out to space. We had the initial 35 units reflected right at the start.
Yep.
We had 17 units radiated directly from the Earth's surface out to space.
Got it.
And now we have 48 units radiated from the atmosphere out to space. So what's 35 plus 17 plus 48?
Let's see. 35 plus 17 is 52. Plus 48, that's 100.
Exactly. 100 units came in and 100 units went back out. The budget balances.
Wow. Okay, that's actually pretty neat how it all adds up. It's a really dynamic equilibrium, isn't it? Lots of moving parts.
It really is. An intricate dance between incoming shortwave and outgoing longwave radiation, with the atmosphere acting as this crucial intermediary absorbing and re-radiating energy.
But okay, even with that perfect global balance, the materials show that different parts of the Earth don't receive or lose energy equally, right? Like the tropics seem to get more than they lose, and the poles lose more than they get.
That's absolutely right. If you look at the net radiation balance of difference between incoming and outgoing energy across different latitudes, there's generally a surplus of energy between about 40 degrees north and 40 degrees south latitude. They receive more solar energy than they radiate away locally.
Okay, energy surplus in the tropics and subtropics.
And conversely, The regions closer to the poles, beyond about 40 degrees north and south, generally have a net radiation deficit.
Hmm.
They lose more energy back to space than they receive directly from the sun locally.
So if that's the case, why don't the tropics just keep getting hotter and hotter year after year and the poles just keep getting colder and colder until they're completely frozen over?
That's a really, really important question, and it highlights another absolutely vital part of the whole climate system. That surplus heat energy from the tropics, it doesn't just sit there and build up.
It goes somewhere.
It gets moved. It's constantly being transported poleward, away from the regions of surplus towards the regions of deficit.
Ow!
Through the planet's large-scale atmospheric circulation, basically, are global wind patterns, and also through oceanic circulation, the major ocean currents. These massive circulations act like a giant global heating and cooling system, a conveyor belt, constantly shuffling heat energy around the planet.
Ah, so winds and ocean currents are moving heat from the equator towards the poles.
Exactly. This prevents the tropics from overheating and keeps the high latitudes from getting locked in a permanent deep freeze. It helps moderate temperatures across the entire globe, making the planet much more habitable than it would be otherwise.
Okay, that makes a lot of sense. All right, so we've talked a ton about energy, heat transfer, balance. How do we actually, measure how hot or cold a place is? Put a number on it.
Right, that's where temperature comes in. Temperature is basically a measure, a degree of how hot or cold something is, typically measured in degrees Celsius, Fahrenheit, or Kelvin. It's related to heat, but it's not quite the same thing. Heat represents the total energy of all the molecular motion within a substance, while temperature is more like the average intensity of that motion.
Gotcha. So what controls the temperature we experience at any specific location?
Well, a bunch of factors interact. We've already hit on latitude pretty hard. The angle of the sun's rays is huge.
Yeah.
Another major one is altitude or height above sea level.
Yeah, the whole it gets colder the higher you climb thing.
Exactly.
Yeah.
There's a general rule of thumb called the normal lapse rate. On average, temperature tends to decrease with increasing height at a rate of about 6.5 degrees Celsius for every 1,000 meters you go up.
Why is that again?
It goes back to how the atmosphere is heated. Remember, it's primarily heated from below by that long-wave radiation coming off the warmed Earth's surface. So generally, the air closest to the heat source, the ground, is warmest, and it gets progressively cooler as you move further away higher up.
Okay, latitude, altitude, what else?
Distance from the sea is a big one. Land heats up and cools down much, much faster than large bodies of water.
Right.
So places right near the coast benefit from the moderating influence of the ocean or a large lake. The water keeps things cooler in summer and warmer in winter compared to places far inland at the same latitude. This effect is called continentality. The further inland you are, the more extreme the temperature swings between seasons and even between day and night.
Continentality. Okay.
Then you have the influence of air masses and ocean currents. If a large mass of warm air moves into your area, temperatures go up. Cold air mass, temperatures drop. Similarly, ocean currents act like massive rivers of warm or cold water. Coasts bathed by warm currents, like the Gulf Stream affecting Western Europe, will be much milder than coasts at the same latitude affected by cold currents.
Makes sense. Currents are like giant heat movers.
Definitely. And finally, you also have local aspects, things like whether a slope faces the sun or away from it. The type of surface cover, urban heat islands, things like that can all influence the very local temperature.
Okay, lots of factors. How do we actually visualize these patterns playing out across the globe? The material had those maps with all the curvy lines on them.
Right, those are called isotherm maps. An isotherm is simply a line drawn on a map connecting all the places that have the same temperature at a particular time, or averaged over a period like a month.
Okay, lines of equal temperature.
Exactly. And looking at maps of isotherms, usually for January and July to capture the seasonal extremes, really helps us understand the global distribution of temperature and see the influence of those factors we just talked about.
So what do the patterns generally look like?
Well, the most dominant trend, as you'd probably guess, is that isotherms generally tend to run roughly parallel to the lines of latitude.
Because latitude controls the main energy input, right?
Precisely.
Yeah.
Latitude's influence on insolation is the biggest control overall. But you see some really interesting deviations from that general east-west pattern, especially where large continents meet large oceans. And the material highlights how these deviations are much more pronounced, much more bent out of shape in the northern hemisphere. particularly in January.
Why the Northern Hemisphere and why January specifically?
Two main reasons. First, the Northern Hemisphere just has way more landmass compared to the Southern Hemisphere, which is mostly ocean. Second, January is winter in the Northern Hemisphere. So in winter, those vast northern continents get incredibly cold, much colder than the surrounding oceans at the same latitude. Remember, land cools down much faster and more deeply than water. So you see the isotherms bending sharply southward over the cold continents like North America and Eurasia, and bending northward over the relatively warmer oceans like the North Atlantic and North Pacific.
Ah, so the lines dip down over land and bulge up over the water.
Exactly. That northward bulge over the North Atlantic is particularly strong because of the warm water carried up by the Gulf Stream and North Atlantic Drift. It keeps places like the UK and Norway much warmer in winter than places at similar latitudes in Canada or Siberia. You might see, say, the 0-degree C isotherm dipping way down into the central U.S., but looping far up the coast of Norway. It dramatically shows that land-sea contrast and the effect of ocean currents.
That really paints a picture. What about July?
In July, it's summer in the Northern Hemisphere. The land heats up much more intensely than the oceans, so the pattern kind of reverses, though maybe not quite as dramatically bent. Isotherms tend to bend northward over the hot continents and slightly southward over the cooler oceans. You see huge hotspots developing over places like North Africa, the Middle East, and Central Asia. But overall, in July, the isotherms tend to run a bit more parallel to latitude globally compared to the extreme bends you see in the Northern Hemisphere winter.
And the Southern Hemisphere, it's more ocean-dominated, right?
Right. Down there, the isotherms tend to follow the lines of latitude much more closely throughout the year. The variations are generally more gradual because the ocean moderates temperature so much you don't get those same extreme continental cold spots in winter or hot spots in summer that you see up north.
Okay, so we see the global averages and the seasonal shifts. What about the difference between the hottest month and the coldest month for a particular place? The annual range of temperature.
Yet the annual range is just that. The difference between the average temperature of the warmest month and the average temperature of the coldest month. And where do you think the highest annual range would be found based on what we've discussed?
Got to be somewhere deep inside those big northern continents, right? Far from the ocean.
Exactly. The material points at the absolute highest annual range, over 60 degrees Celsius in some spots, is found in the northeastern part of the Eurasian continent, think Siberia.
60 degrees Celsius difference between average summer and winter temps. That is just extreme. It's hard to even wrap your head around if you live somewhere milder.
It really hammers home that continentality effect. Far from any moderating influence of the ocean, those huge land masses just bake under the long summer days and then radiate heat away relentlessly during the long, dark, frigid winters. The temperature swings are enormous.
And where's the smallest range? Near the equator.
Yep. The lowest annual range, maybe only around 3 degrees Celsius or even less, is found near the equator, generally between about 20 degrees south and 15 degrees north latitude. Because down there, the amount of incoming solar radiation doesn't vary nearly as much from season to season, and temperatures stay pretty consistent year-round.
Okay, one last thing. We talked about temperature usually decreasing with height, that normal lapse rate. But you mentioned sometimes the opposite happens, right? It gets warmer as you go up.
That's right. It's called a temperature inversion, or sometimes just an inversion. It's literally an inversion of flipping of the normal pattern. For a certain layer of the atmosphere, temperature actually increases with increasing altitude.
How common is that?
It's usually a fairly shallow temporary situation near the ground, but it's actually quite common, especially under certain conditions. A classic type is called a surface inversion or radiation inversion. It forms most readily on long, clear, calm winter nights. What happens is the ground loses heat very rapidly by radiating it away to space. Clear skies let the heat escape easily. The ground gets really cold.
Colder than the air above it.
Much colder. And through conduction, it chills the layer of air directly in contact with it. But the air just a little higher up doesn't cool nearly as quickly. So by early morning, you end up with this layer of very cold, dense air right near the surface with warmer, lighter air sitting on top of it. That's your inversion. This kind of setup is also pretty much the normal state of affairs year-round over the very cold polar regions.
Okay, so you get this lid of warm air over cold air near the ground. What are the effects of that?
Well, the main thing is it creates extremely stable conditions in that lowest layer. Because the cold air is dense, it doesn't want to rise, and the warm air above acts like a lid, preventing vertical mixing.
So stuff gets trapped.
Exactly. Any air pollutants, smoke from chimneys, exhaust from cars, dust released near the ground, get trapped underneath that warm inversion layer. They can't rise and disperse, so they just spread out horizontally, often leading to really dense fog or smog building up, especially common on those cold, still winter mornings. The inversion usually breaks up once the sun comes up and starts warming the ground again.
Nasty stuff. Any other kinds of inversions?
Yeah, another common one happens in hilly or mountainous areas, often called air drainage or a valley inversion. At night, the air on the slopes cools down rapidly. Because cold air is denser, it literally flows downhill under gravity, like invisible water, and pools in the bottom of the valleys.
So the coldest air ends up in the valley bottom.
Yep, the warmer, lighter air gets displaced upwards or stays higher up on the slopes. So you can end up with this strange situation where the valley floor is actually colder than the hillsides partway up. This can sometimes even protect crops or orchards planted on the slopes from frost damage because the coldest air has drained away below them.
Wow. Okay, from the journey of a single ray of sunlight hitting the top of the atmosphere down through scattering and absorption, heating the ground, warming the air, creating global budgets, driving winds and currents, shaping temperatures worldwide, and even causing these weird upside-down temperature layers in valleys. We've really covered a lot of ground.
We certainly have. And understanding this, this intricate dance of energy coming in, being absorbed, transferred, redistributed by winds and currents, and then radiating back out.
Yeah.
It's just absolutely fundamental. It really is the engine behind virtually every weather pattern and long-term climate feature we experience on Earth.
So what does this all boil down to for you listening? Well, hopefully the next time you feel the warmth of the sun, or maybe you notice how much warmer the sand is than the water at the beach, see that brilliant blue sky, or perhaps shiver through a surprisingly cold, foggy morning down in a valley, you'll have a little more insight into this incredible, invisible energy system that's constantly at work shaping the temperatures all around us. It all comes back to the sun and Earth's amazing balancing act.
And it really does make you pause and think, doesn't it? If this whole planetary temperature system is based on such a delicate balance between incoming and outgoing energy, and we've seen how critical the atmosphere's composition is for absorbing and radiating that energy, well, it raises the question, how might even relatively small changes we make to the composition of that atmosphere, like, say, adding more of those heat-absorbing greenhouse gases, potentially ripple through the entire system and perhaps alter that fundamental balance over time? It's certainly something to ponder the next time you look up at that vast atmospheric ocean above us.
Absolutely. A really crucial point. It just underscores how interconnected everything is in this incredible system we call Earth. Hopefully this deep dive gave you some real aha moments and maybe a handy shortcut to feeling well informed on this really fascinating topic.